Namaskar, welcome to channel. Give just 5 minutes and watch high school math come alive. Pure visuals, lasting understanding. We will not only understand why the permutation of 4 objects is 4 factorial, but also understand why the permutation of 5 is 5 factorial, but also understand why the permutation of n object is n factorial. We use the following example, but the idea extends to any arrangement of 4 distinct objects in 4 distinct positions. Consider the 4 books: a math book, a science book, a history book, and an English book, as illustrated. Then consider 4 shelves: a yellow shelf, orange shelf, green shelf, and brown shelf, as illustrated. Our goal is to arrange these 4 books, math, science, history, and English, onto 4 shelves, with the order of placement being important. We aim to place each of the 4 books onto 4 shelves, ensuring every shelf holds 1 book and all 4 books are used in each arrangement. Thus, each arrangement consists of 4 shelves, each occupied by one distinct book. From this point forward, we will always treat the 4 shelves as a single unit, emphasizing that each arrangement is counted every time all 4 shelves are filled. Placing only the math and science books in the first 2 compartments does not constitute a valid arrangement, as all 4 books must be placed in each of the 4 compartments. However, placing the math, science, English, and history books into the 4 shelves results in a valid arrangement, as all 4 shelves are filled. This is also an invalid arrangement, as placing 2 identical books in the same arrangement is not allowed. There is another valid arrangement, and now we will explore all possible such arrangements. This is a permutation problem, as swapping the positions of the books creates distinct arrangements. In combination problems, the shelves become indistinguishable, as shown here with the same color. In this case, swapping the positions of the books does not result in a new outcome. This is one outcome, and interchanging the positions of the books does not create a new arrangement, as it remains the same outcome. Let's list every way to put the 4 books on the 4 shelves, where order matters. There are 4 factorial equal to 24 such arrangements. First, we list all books available for the first yellow shelf along the x-axis. Then, we list all available choices for the second orange shelf along the y-axis. And we continue similarly for the remaining shelves. Let us begin by placing available books first from yellow or first shelf. There are 4 groups, each consisting of 4 shelves, because there is 4 choices of books to choose for the first shelf. For the first yellow shelf, there are 4 possible choices. We can place either the science book, history book, English book, or math book. This gives us 4 possible ways to choose a book for the first shelf. After placing the books on the first yellow shelf, we move to the second shelf. Since one book is already on the first shelf, only 3 books remain for the second shelf. The second shelf is along the y-axis, so we now place the 3 available book choices vertically, representing all combinations for the second shelf. If the science book is placed on the first shelf, then for the second shelf, we have 3 remaining choices: the math, history, or English book. Thus, there are 3 possible choices for the second shelf when the science book is on the first shelf. Therefore, once the science book is placed on the first shelf, we have 3 possible ways to fill the second shelf with either the math, history, or English book, completing the arrangement for the first 2 shelves. Similarly, when the history book is placed on the first shelf, we again have three choices for the second shelf: the math, science, or English book. Thus, just like before, there are three possible choices for the second shelf when the history book is on the first shelf. Similarly, in the scenario where an English book is on the first shelf, we again have three books to choose from for the second shelf. This is why there are three possible arrangements for this specific case. If the English book is placed on the first shelf, then the available choices for the second shelf are either the math book, science book, or history book, and again three possible choices as before. Similarly, if the math book is placed on the first shelf, the available choices for the second shelf remain the same: the science book, history book, or English book. Let us recap what we have done so far. The first shelf is open to any one of four books. For each of the four first shelf picks, the second shelf still offers exactly three options. While the titles depend on the first choice, the count stays the same, which is 3. Therefore, we multiply 4 by 3, giving 12 distinct ways to place one book on the first shelf and one on the second. Another view is adding 3 plus 3 plus 3 plus 3 to get same 4 multiply by 3 to understand why we multiply to find total outcomes of placing two books. Let us now proceed to fill the third green shelf. The process of filling the shelves with books can be likened to calculating the volume of a rectangular parallelepiped. Here, the length corresponds to the number of choices of books for the first shelf. The width represents the number of choices for the second shelf, and the height reflects the number of choices for the third shelf. Each dimension is directly tied to the respective shelf's available book options, and this analogy elegantly captures the essence of determining the total number of possible book arrangements. Thus, the volume of this parallelepiped is equivalent to the total number of possible outcomes for filling the first three shelves with the four available books. Each dimension represents the number of choices for the respective shelf, and the product of these choices gives the overall count of possible book arrangements. So far, we have calculated the number of ways to place four books onto the first two shelves, much like evaluating the base area of a parallelepiped. Now, let's determine the number of possible arrangements and which books are available to be placed on the third shelf. To do this, we need to stack the first and second filled shelves. The books chosen for the first and second shelves will dictate the available books for the third shelf. The third shelf's choices are constrained by the books already placed on the first two shelves. Since two books are already placed on the preceding shelves, there are only two books remaining for placement on the third shelf. Interestingly, this number of available choices also corresponds to the height of our parallelepiped, as discussed earlier. The remaining books for the third shelf are determined by the books chosen for the first two shelves, ensuring that only two options remain for the third shelf. For the third shelf, there are two choices of books, since two books are already in place and we begin filling from the backmost shelf. Thus, if the science and history books occupy the first two shelves, the third shelf can be filled with either the math or the English book, resulting in two choices. Then we move one layer upward and fill the third shelf with the two available books. In this case, if the science and English books occupy the first two shelves, the third shelf can be filled with either the history or the math book, resulting in two choices. Eventually, we move to the first layer where the science and math books are placed on the first two shelves. For the third shelf, we have two choices: either the history book or the English book. Let us now observe the list of all possible fillings for the third shelf simultaneously when the science book is placed on the first shelf. Similarly, now whenever there is history book in the first shelf, we begin filling third shelf, each with two choices of books beginning from the backmost shelf. We then gradually proceed one layer upward, duplicating each arrangement into two. For each of these duplicates, we place the remaining two books into the corresponding shelves. As we move upward, each arrangement branches into two possibilities, with the available books being placed in the third shelf, ensuring that all possible combinations are covered. This process ensures that all potential outcomes are accounted for by systematically distributing the remaining books across the shelves. Similarly, now whenever there is English book in the first shelf, we begin filling third shelf, each with two choices of books, beginning from the backmost shelf as we have been proceeding. All the layers are shown here simultaneously. Watching them multiple times will help clarify the process, but the general idea remains the same. As we move upward through each layer, we duplicate each arrangement and place the remaining books on the third shelf. This step-by-step approach ensures that all possible combinations are considered and displayed, providing a comprehensive overview of how the books can be arranged across the shelves. Similarly, now whenever there is math book in the first shelf, we begin filling third shelf, each with two choices of remaining books. Thus, there are 4 into 3 into 2 is equal to 24 available possibilities for arranging the 4 books across the 3 shelves. This reflects all the possible outcomes based on the choices available for each shelf, and by multiplying the number of choices for each shelf, we arrive at the total number of possible arrangements. Finally, we come to the last shelf, which has only one choice of book available. This is because all other books have already been placed in the previous shelves, leaving only one book to be placed on the final shelf. Start with 4 choices for the first shelf. For each, there are 3 choices for the second. For each of those, 2 choices for the third, and finally only one for the fourth, giving 4 times 3 times 2 times 1 equal to 4 factorial. Just as arranging 4 objects gives you 4 choices for the first spot, 3 for the second, 2 for the third and 1 for the last, the same logic applies to arranging n objects. We have n choices for the first position, n-1 choices for the second, n-2 for the third, and so on until only one choice remains for the final spot. Therefore, the total number of permutations is the product of these choices, n times n-1 times n-2 up to 1, which is exactly n factorial.